Hi, my name is Adam Stiff, and I'll be talking about how a simple self-attentive model helped with rare classes in our virtual patient question-answering dialogue agent. So this is Carlos, and he is our dialogue agent. He's a patient who has come to the doctor to hopefully receive some treatment for some fairly serious back pain. He's currently configured to help physicians practice interacting with patients who have limited English speaking proficiency, but his usual use is to help first-year medical students learn how to interview real patients. Having a virtual patient instead of a human addresses a lot of issues like cost, consistency, and availability, but it introduces the technical challenge, of course, of understanding natural language inputs. We model each conversation as a sequence of context-free questions, and we always provide fixed answers to make sure that students are receiving the correct information from the patient. So really, this is a semantic classification task where we're mapping single utterances from the students into a set of questions that the agent knows how to answer. The patient has answers for over 350 unique questions, so we're trying to directly classify the inputs as one of those 350 plus classes. What really complicates the problem for us is that the distribution of the frequency of those classes is very skewed. We have a data set with about 10,000 examples, and you can see here that the most frequent quintile, shown in red, is comprised of less than 10 classes, but there are like 250 classes in the least frequent 20% of the data. The previous best approach to this problem used an ensemble of ensembles of text CNNs, which worked very well on the frequent classes, and then we combined that with a rules-based dialogue engine that did better on the infrequent classes. Now for this project, we wanted to do as well as we could with a single learned model. So by treating this as a standard classification problem, we've basically assumed that all of our classes are totally orthogonal to each other, but we know that's not true. There are a lot of classes in our data that have a lot in common, such as, do you have any medical conditions, and have you ever had any serious illnesses? So the main distinction between those two classes is the tense of when you had or do have a medical condition. But everything else about those questions is very similar. So we wanted to leverage this kind of structure in our question set to learn parts of frequent questions that can successfully be transferred to improve performance on related rare questions. And we thought that multi-headed self-attention mechanisms might help us here, because ideally each attention head could learn to focus on distinct semantic aspects of the questions, and then hopefully learn to generalize those semantics across classes. The first thing that comes to mind when talking about self-attention, of course, is BERT. Realistically, a full-fledged BERT model is probably too slow to use for a real-time application like ours, but it has given great performance on many tasks, so we wanted to see how it did for us. Our first pass was a standard fine-tuning setup where we just sent the CLS token from BERT into a fully connected layer and fine-tuned the whole BERT model for our classification task. Surprisingly, this did not outperform our baseline CNN model, which for comparison was just one of the CNNs out of our previous ensemble of ensembles approach. You can see that the accuracy was just a little shy of the CNN with glove inputs, but the macro average F1 score takes a big hit, indicating that the BERT fine-tuning approach is really underperforming on the rare classes. And that is really the opposite of what we want, so we also looked at a smaller, simpler model that utilizes self-attention from researchers at IBM and MILA. That model consists of an RNN equipped with a self-attention module that produces multiple attention weights per time step and uses those weights to aggregate the hidden state representations from the RNN into multiple attention head representations, and then concatenates and classifies the multi-head representations. So this model did beat the baseline on overall accuracy, and it did so by substantially improving on the rare classes, as you can see with the big improvements on macro F1. And just to emphasize that, here's a chart showing the accuracy of the RNN model versus the CNN baseline for each quintile of the test data. You can see that the rarest classes show the most improvement. So that raises two big questions that constitute the bulk of our contribution here. Why doesn't BERT help for our virtual patient task? And why does this self-attentive RNN help? To answer the first question, we ran a couple of experiments that attempted to control for the architecture of the classification model. Basically, we took hidden layer representations of individual word tokens out of a raw BERT model and fed them into our existing CNN architecture. We tried a few different layers from BERT, and surprisingly, the first layer worked the best for this. So for one experiment, we just used the fully contextualized representations from that layer, and for another experiment, we averaged the contextualized representations over the whole training set. They both did worse than the fine-tuning result, but the average representations did a little bit better on rare classes. Our intuition about this is that the BERT model has a lot of freedom to represent similar word semantics nearby to each other in the representation space, but not exactly the same way. When you don't have many examples to train your downstream classifier, then it's hard to learn the full variability of what can come out of the BERT representations that's relevant to your classification task. To try to understand why the self-attentive RNN helped our performance, we did a couple of things to visualize the attended representations directly. We inserted bottleneck layers with sigmoid activations after each attention head that produced an easily visualizable low-dimensional representation. This allowed us to see easily not only what each attention head was looking at, but also how it was representing it relative to other sentences. So one compelling example that we found this way is the three classes: do you drink, meaning do you drink alcohol, and do you drink coffee, and do you drink enough fluid. The do you drink class is very frequent and the others are rare, so the trigram do you drink is highly correlated with the alcohol class, and the CNN almost always misses the other two classes in favor of the alcohol class. The RNN does pretty well at this distinction though, and this diagram here shows why. We gave each attention head an arbitrary color, and the opacity of the underline under each token shows the attention weight for that head at that token. Then over to the right, each row shows the bottleneck activations for the sentence with the same colors for each attention head as in the underlines. What we can see is that several attention heads, yellow and green for example, are consistently focused on the verb drink in these sentences, and that token is getting represented very similarly across these classes. Meanwhile, different attention heads learn to focus on the object of the drinking, and those representations are distinct for these classes. So what was extra interesting was that when the object is implicit, as in this second example, those object-focused heads attend to the verb instead of the non-existent object, but they still represent that token the same way they represent alcohol when it's explicitly mentioned. So it seems to be explicitly representing that implicit meaning of drink, and we thought that was very interesting. I think that's about all I have time for. We do have further analysis and examples both in our paper and in my dissertation that support the claim that this self-attentive RNN is able to leverage structures in frequently occurring classes to improve performance on rare classes. So I hope you check it out. Thank you all for listening, and I look forward to your questions.